So like, is this on? Yeah, it's on. Okay, cool. Wow, this is cool. It's great to be here with all of you. You know, as Neela said, in the early days of Open Daylight, it was the 7 by 24 Open Daylight all the time. And over the last couple of years, I haven't been working directly on Open Daylight. So I'm glad to be here and glad to see all of you. And I'm honored to be talking to you today. This is sort of the science fiction part of the agenda. Not so much fiction, but you know. So let me just dive into this, and let me just say up front, I have way too many slides, but I always have way too many slides. You guys don't have to take notes or pictures or anything like that. You can have the PowerPoint or you can have the PDF. There's a pointer to the URL there, and if you can't get it, just send me an email and I'll get it for you. So let me dive into this a little bit, and let's talk a little bit about what's going on here. So title is about, you know, applying recent advances in machine learning to networking. In the network space, we're way behind sort of the cognitive applications like image processing and things like that. So we have a ways to catch up, but things are really happening. So let me just dive into this. So I always show this picture because, you know, this is what my mom thinks I do. It's like Terminator or something like that. You know, it's like AI. Okay, what is that? And then, you know, at work, in my work life, it's really more like this. You know, somebody goes, hey, we got this data, and I'm looking at it, and I'm going, what is this? And they go, you know, sprinkle some machine learning pixie dust on it and do something fancy with it, you know, and it's like, I'm going, what? And then the reality of it is this, you got to do the math. At the end of the day, that's what it is. Machine learning is really focused on implementability, and that's good for us because we like to write code. So I just want to spend one slide on this. Back in the day, it was hydrogen. That was kind of my era, hydrogen, helium. And I just want to congratulate all of you on boron. It's incredible the way the community has grown and come together and the quality of the work that you're all doing. So give yourself a hand. Really great. It's impressive. So I see I have 18 minutes left, which, you know, 3 minutes per slide. I should be able to do 2 or 3. So here's some things. I just wanted to tell you this up front. You know, so like I heard this at the Spring ONUG, this fellow from Sequoia Capital just offered this not in a machine learning segment, just he was on a panel. You know, it's going to drive public cloud and enterprise. I heard Chris Wright on an interview on theCUBE with Dave Ward, and he offered this one, right? Okay, automating your automation. That's not untrue, that's true. But what I want to remind you all is, like every other technology, you're actually kind of like here, right? And so be a little careful. When you're starting to engage this technology, be skeptical and you know, use your judgment and try to avoid the hype because the hype cycle is really, really going right now. So here's my agenda, and we're not going to get to all of this. I'll edit it on the fly based on what that clock's telling me. And there's some code and stuff there at those URLs. You don't have to copy them down. You can get the deck. So what is it? Well, this is Andrew Ng. Andrew Ng is a professor at Stanford. He was a co-founder of Coursera with Daphne Koller, founded the Google Brain Project, and is now chief scientist at Baidu, big machine learning shop. And basically what he says is, you know, when we write code, the complexity of the code we write is generally in the code. Here, the complexity is in the data, and the code is in principle simple, and I'll show you a little of this later. But this is Andrew. And if you want to say it a different way, when we look at the data that's coming off our network, we just kind of envision that there's a process, a data generating distribution sometimes, and it generates the data we observe. We're trying to learn that, call it a function, right? And we really care about the generalization of that function or model much less than we care about how we do it like when we're training it, right? Because when you're training things, you could just memorize it, right? So we want accuracy on examples that we haven't seen yet. How can that be possible? Now think about that. There's a reason. And you can do this wrong, and you can get fantastic accuracy when you're training and crummy accuracy when you have real data. So we have, you know, it takes some skill and art. Here's the cartoon of the same thing. So when we write programs these days, you know, like I'm writing a router, it gets a packet, I process the packet, and I output the packet, right? And so I get data, I have a program, it runs on a computer, and I have some output. Packet gets forwarded on some interface. Machine learning, especially in the supervised setting, is different. You get data, and you get the output, and you output a program that tries to recognize this function. I just call it F here. Now, this is supervised learning. There's also unsupervised learning where you just get the X's. You don't get the output. This is much harder, and this is kind of the frontier. And then you can also learn in sort of a trial and error way from interacting with your environment, which is also, it's called reinforcement learning. This is also happening right now all around you. So that's kind of, the high level of what it is. So like, when would we use it? Why don't we just write programs to do this stuff? Well, when patterns exist in our data when we don't know what they are, or if they might be noise, right? We don't know, and so we need to use this kind of technology to figure that out. We'd like to use it when we can't, kind of figure out what the functional relationships are mathematically, because of course, if we could do that, we could just code it up, right? And we use neural networks. I'll show you what a neural network is in a second, for function approximation, and we need this to make all of this scale. Because remember, this is all working on massive data sets, because you can think of what comes off your network. It's quite a bit. It's also when we have lots of unlabeled data, this is where it's just raw data. And the data becomes really high dimensional, and I'll explain that later. But if you think about 4K television, the pixel space for 4K television is almost 9 million dimensional space. And I have hard enough time in 3 dimensions, and most people, like I walk into things all the time, and so, and when it gets to be higher than 3-dimensional, I'm not really sure. Maybe Einstein could do 4. But we also want to discover lower dimensional representations of that data, because there's computational costs to this high-dimensional stuff. So we try to get the dimensions to come down. And I'll explain a little bit about that if I can get to it. And I'll just say this is important for us, because machine learning is really heavily focused on implementability. Like, if you have some fancy machine learning algorithm and you can't implement it, come back later. Fail, right? So basically, there's lots of open source code available, and I'll tell you right now that in the networking space, the machine learning space has a long history of open source, open code, open source, open data, and even open models. So it's really a kind of an open science environment that we're working in. So it's kind of just like what we're doing here. It's not so focused on the community building that we have here, but things like TensorFlow, and I'll show you some code in TensorFlow in a bit. That's the Google machine learning framework. Torch is Facebook. So then there's many others. What kind of problems would we do? Well, we wanted to do pattern recognition, and we might want to do faces, we might want to do handwritten digits, medical images, sensor, IoT data. We might want to build recommender systems where what we do is we learn what is going on in the data and then try to recommend to the operator perhaps what would be good ways to optimize the network or mitigate things like anomalies. We want to optimize, this is big in orchestration right now, we want to optimize the behavior of the VNFs, right? We want to, this is a little bit more than we do, but you can actually build what's called a generative model that will give you new examples of the data that you've seen. Anomaly detection's huge. This is all about either recognizing patterns that are anomalous in your equipment, in security applications, and so forth. And then you might want to predict the future. Now, I'll just tell you, this predicting the future thing is like, well, the past is usually a good predictor of future, and in that sense, this can work. But there's no magic. Can't predict the future, really. Unless, of course, the past is a good predictor. Okay, so why is this hard? I mean, why don't we just do it? Why is it new? What's up? So suppose you have an image. These are my granddaughters some time back. You see this, right? And you go, oh, wow, that's great. Well, really what your machine learning algorithm is going to see is, just a bunch of bits. And the question I'm going to ask you is, what's in that picture? How do you write a program to do that right now? Well, the answer to that is you really can't. You need machine learning to do it. So here's another view, like, what's a 2, right? So the green ones, the things in the green box were actually correctly classified as 2s, and the ones in the red weren't. Are they that different? I mean, you got to really be sharp to get that, right? So how hard is it actually to do that? Now, I'm going to give you an example that's based on, well, here, let me show you. This database is called MNIST. They're 28 by 28 handwritten grayscale images, so they look like this. I just printed out the first 9 here. The reason I'm using these is because I can visualize it. If I visualize network data, you won't know what it is. It's just because it's not in something you'd recognize. So here, The features that we're interested in are the pixels, and they're 28 by 28. So already we're at 784 dimensional space here. Now, in the network or in other KPIs, where's Chris Metz? He caught the bug in that. It's the same process. It's just different data sets, right? So when I'm showing you this in the digits, just think of it as like I got a big vector of net flow data, or I have KPIs from cache management, from CPU management, or whatever they are. So the features in that case are various counters that you might find in your network, and other KPIs that you get out of the server space, perhaps, or other spaces that are interesting to you for orchestration and other purposes. So the same thing will work there, but this is easier to see. Okay, so one way to recognize these things is to use a special kind of neural network, right? And so this neural network is called an autoencoder, and basically what it does is it takes the input, squeezes it into this hidden layer, and then blows it back up. And then what you do is you just look at the difference between the input and the output, and you try to minimize the error in that, okay? And so the key thing here is that this hidden layer, see where it says hidden, it has fewer units than the input or output. So it's about compression in some ways. And by the way, at some very deep level, learning actually is about compression. So the one I built was like this. Remember that the digits were 28 by 28, so that's 784. I used 100 hidden layers, so I'm compressing it that much, and then blowing it back up to the size it was before. And this is unsupervised, by the way. So before I do this, what does one of these neuron things do? I mean, what's really amazing about this is, so the picture is sort of stylized on the right there. This is what one of those things does. It takes its input, it just sums them up with these weights, and then maybe applies a function to that. And then what you do is you just arrange these things in such a way, that's called the architecture of the network, that is either like an autoencoder like this thing, or in other ways. But they don't do anything else. So they just add up the weighted sum of their input. And adjusting the weights to get the minimum error, and I'll show you this in a second, is what learning really is. So this is what we want to do in our network, right? So this is the sum, just something to show you that it's not magic. You just add it up. And this is the function. It's called sigmoid. What it does is it squashes, sometimes called squashing, squashes the input into the range 0, 1. So that's kind of nice, because if you want probabilities, they're in 0, 1. So it kind of looks like this. And that's what this thing does. Oh, by the way, anybody have any idea of how many parameters this little tiny thing might have? This 784, 100, 784 one? Well, here, let's just do it. It's 784 times 100, because there's 100 weights between, or there's 784 inputs, and then there's 100 hidden layers, and each of them has a weight. And then going the other way, there's 100 times 784. So there's about 157,000, which means in order to run an example through here, you have to do 157,000 operations. So think about that. It's all cool, but how does it really work? Well, here's how it works. The encoder is just some function. And what you do is you encode the thing into the 100, remember it's 100 wide, and then you hand that to a decoder, and then you just compute how well you did. So it looks kind of like this, right? So this is the thing I was showing you on the other page, but the important thing is the loss function there. You just subtract the two vectors, and then this is called the minimum squared error, but this is just a typical thing. So it gives you the average error. That's it. And then you try to minimize that, and that's how this thing learns. So here's the code that does it. How hard to do it in TensorFlow? How many people have heard of TensorFlow? Because it's a Google thing, right? It's just a framework for doing this. If you have time, it's pretty interesting. It does graph computation. So you build this computation graph and then hand it to the back end that actually does the computation. So none of this is actually doing the computation. It's setting up the graph. But you can think of it as doing the computation. And anything that says TF on it, TF dot anything, that's a TensorFlow operation and becomes a node in this graph. So here's the encoder. You can look at it. All it does is it does exactly this operation. It adds the dot product of these two things to what's called a bias. You always put one bias in, so it'll turn on some of these neurons. And then, if there's a nonlinearity like the sigma thing, I just made it parameterized. Then you return the code, which is the encoded version, so like in this picture in the middle. So not very hard, really, right? And then when you want to decode it, you just hand the output of the encoded thing to the decoder and tell it to decode it. And then finally what you do is, oops, can I go backwards? Oops, maybe this. Yeah. Then finally what you do is you calculate the loss, and then you try to minimize that. And TensorFlow has all kinds of infrastructure for doing this minimization. Again, you don't have to do this. When I started doing this 3 years ago, you'd have to write that code yourself, which is tricky. And today you don't. You just use TensorFlow, Torch, any one of these things. Okay, so what happens? So check this out. Now imagine this is why I'm using the digits instead of network data, because network data you wouldn't be able to make any sense out of it because it doesn't correspond to something that's in your experience. So if I just give it one example, the MNIST data digits that it had are on the top, and the reconstruction, you can see it's just random, right? Because you initialize the weights to random, right? And then if you give it 10, it gets a little better, and if you get 100, it's a little better. But by the time you give it 1,000, it's doing pretty well, right? And so what happens is it gets low reconstruction error, and on things from MNIST, and well, I'm running out of time already. On things from MNIST and everything else, it gets high reconstruction error. So you can see how you can use this for anomaly detection. If you just put a threshold above which the reconstruction error goes, you call it an anomaly, right? And we can do this in networking too, which we do, by the way. Okay, so I'm going to skip this because I have like 3 minutes. Let's see what else is interesting in here. Well, I'll just tell you this. There's a lot of beautiful mysteries in here, and if you want to look into these or you want to talk about these, just send me an email and we can talk about it. A lot of beautiful things in there. Let's see. I'm going to kind of skip this because you probably have seen all these things. I want to show you the SDN piece of this. Okay, this is history too. I put all this stuff in here because I want you to know it, but I'm editing it. So this is the kind of use cases we've been working on. Security anomaly detection, kind of what Google calls SRE, NFV orchestration and optimization. Some new tools we built for DevOps, I can show you those later. Just come find me. I'll be here for a couple days too, so just come find me. And other applications like this. Okay, so here's the thing. So what's great about SDN is that SDN has made all of these things actionable in the network because now we can program it. So we did this work called knowledge-defined networking, and basically what this thing comes down to is you have some, this thing doesn't have a, okay. You have some analytics platform, it's getting data from the network, you clean it up. By the way, cleaning the data up that you get out of the network is about half the work here. It's really difficult. Network data is noisy, it's just not very nice stuff. And then you apply machine learning, and then you might have some automated decision making, or you have a human in the loop. And you might have an intent language, that's a, and then you just hand that to the SDN controller, and it does something, and you go around in this loop. And I'll just note right here that the SDN controller and the intent language itself is hard-coded actions, right? And so there's some of this that's hard-coded. You're not really learning something here that you want to learn. So the kinds of applications are recommender systems, optimization, estimation of performance and cost, validation of designs, and other kinds of knowledge discovery that we've been looking at. So here's a good, well, I've got about 1 minute left, but I want to show you this example. So what I want to do is I want to learn optimal paths in an overlay network, but I don't own the underlays, so I want to see if I can figure out what are the best paths in terms of minimum delay in a network. And essentially the goal here is, like, should I go from A to C or A to D, or what should I do? And basically the goal is to achieve minimum delay between the overlay nodes. Common problem. Well, this is details, but this actually we actually did this experiment. It actually worked pretty well. I don't know if service providers are going to love this, but you can learn it. And this is showing you that if you have more examples, you can get better error properties with it. This is the system. Okay, 40 seconds. So here's one other thing that you might notice. So here's the thing I was showing you, this kind of canonical machine learning sort of setup, right? In here, all of this has hard-coded logic in it. We really want to learn that. And that's what reinforcement learning is about. How many people have heard of AlphaGo? There's this poor fellow, Lee Sedol, who was like a Dan 9 plus Go player, and he got beaten by AlphaGo. And this picture on the lower right here, or I guess it's your lower right, is a picture of these racks of TPUs. These are TensorFlow processing units at Google that beat this guy. So I don't know, I don't know if it was exactly fair, but it's pretty impressive what they did. And all this is about is in reinforcement learning. Oops, I'm out of time. In reinforcement learning, you have an agent. It can take some action. It learns from its action. That's the trial and error thing. So these are applications we can do. Let me just go one more. So here's the summary. There's lots of network data. It's coming off the networks that you guys build or that you find in the controller, like the various data sources in the controller. There's lots of open source frameworks today. TensorFlow I talked about, Torch is one of them. There's many of them. This table has a bunch of them. But it still requires some skill and experience to build these things. And I'll just tell you right now that this is going to be a part of your life. You're going to see it in all facets of networking and everywhere else for that matter. We're already seeing that. And so all of that said, now's the time to get your feet wet because you can write code that does really interesting things in these frameworks without having to spend all of the time learning how to do these fancy algorithms. So with that, I think I don't know what I have left. Yeah, and if you have questions or comments, just send me an email. I'm always available. Thank you.